So let's see the effect on output impedance. So can anybody intuitively tell what will be the output impedance, the DC output impedance in this? So what is the impedance looking into the output node?
Very small as the source of the
1 by GM because
1 by GM, but what about the feedback?
yeah, so that will be divided by 1 plus A beta as we saw in the other for closed loop
Yeah, so
at DC.
if this is A naught 1, where A naught 1 is sorry, GM1 times R gate, so it will be divided by because your source follower, I mean, ideally you will have a gain of unity. So there'll be no gain from the source follower. So your GM will be divided by 1 over GM will be divided by this GM1 R gate. So let me call it GM2. So that is your AO1. R out open loop is approximately 1 over GM2 and R out closed loop is approximately 1 over GM2 multiplied by AON, which comes about GM1. Okay, so this is obviously much less than R out, where R out was parallel combination of all the output resistance. So R1 plus R2 plus R load plus R out of your transistor. Okay, so that's what we had. So 1 over GM2 is obviously much less. So in that case, it will be much less. So let's see what happens. So if let's say my pole is at the gate, so assuming dominant or omega P gate is dominant, then what would happen? So what will be the starting point? So let's see the open loop. What will be the starting point for open loop?
1 by GM2.
1 by GM2. So in the open loop, where will be the pole? Where is the pole? Can anybody tell where is the pole in the open loop?
M by C out.
Yeah. So this is your omega P out. Let me change the color. So this is your open loop. Now with the closed loop, what will be the starting point? 1 over GM1, GM2, R gate. And now your
Sir, we
pole
are
is,
taking beta 1, I mean, for simplicity.
sorry. Okay, let me just add beta also. So this will be your beta. Okay. So you have, so if this is your omega p gate, so it will remain flat. So what would happen after omega p gate? It will start increasing or decreasing?
It start increasing, right? For omega p gate dominant.
Yeah, and let's say this is your omega UGB. If this is my omega UGB, so roughly, can you tell what will be the at omega, around omega UGB? Okay, and then it will follow the because now your loop is broken. So your beyond UGB, your response will look similar to your open loop. So you will be mostly depending on your out for this drop in the output impedance. So if I compare this one with PMOS, can we tell this looks better or worse or similar to PMOS?
Was
Why was?
we usually expect flat curve, and the flat curve
No. Take the same condition. The PMOS with the dominant pole at gate. So omega P gate is dominant. How was the curve with the PMOS? Do you remember? What was the maximum impedance it was going to around UGB? Anybody remember?
R not, sir.
Okay. Let me open the. So this was your PMOS, correct? And this was going to R out. So you 1 plus beta naught is a loop gain. But here, and since around UGB your loop will break, so after UGB it will follow the open loop curve, and that's why you hit the R out. But here the peak is 1 over GM2, and 1 over GM2 is much less than R out. So I can say that output impedance. So output impedance of NMOS LDO is compared, or I can say lower compared to PMOS LDO. Okay, so what does it mean? So which parameter will be, or in terms of performance, which parameter will be better than MOS?
Transients,
Load
low
So
transients,
load,
low regulation.
load transient is better. Is better. And second point. What about the DC? DC impedance? Is it better or worse? Or same? Mm-hmm.
It is better.
Why?
Uh,
Why better?
the same reason, because R out is 1 by GM2 right here. So it is lesser. So that again divided by A naught. Okay, the gain will be lesser in this case. Okay.
Yeah, so because in the other case you had output gain in your loop gain, so R out will be get cancelled out. Okay.
Mhm.
So R out over beta I naught is nothing but R out over beta GM1 GM2 R gate R out. This cancels out. So what you get is the same. Correct. 1 over beta GM1 GM2 R gate.
Yes, sir.
Okay. So because you don't have any gain in the output stage, so DC output impedance looks similar until unless you have a higher gain in the error amplifier, and that will be in most of the case that's what you will have actually. So because your loop gain is completely determined by your first stage, which is error amplifier, while in PMOS, your total loop gain is determined by two stages, your error amplifier as well as your PMOS output stage. So let's say your 40 dB is coming from first stage and 20 dB coming from your second stage. So total you will get 60 dB. In this case, if you have only 40 dB in the error amplifier, then total loop gain will be roughly 40 dB or less, which may not be acceptable. So you have to use there is no option but have to use a high gain error amplifier, so 60 dB. So in that case, okay, you can say that that will be better. But if you talk about the same error amplifier gain, then there is no change. So same DC output which I can say load regulation. Small signal load regulation, obviously, I'm not talking about large signal here. But when you define your load regulation, you look at the entire range of the load. So DC output impedance is same for same gain of which we call it AO1. Okay, but if you look at the high frequency response, your magnitude looks smaller. So you can say that obviously your line transient, load transit will be better here. Okay, let's talk about the PSRR. PSRR. So let's copy this. Okay, can anybody intuitively tell what will be the effect on PSRR? So now you are applying your input signal at Vin, the AC input, and you are looking at the output. So V out by Vin will be your transfer function.
No effect.
So no effect. Why no effect?
My gain is GM into VGS, and input voltage is connected to drain. So
Sorry. So what are the different current paths from V in to V out? So in the PMOS, we have the GM component. Do we have a GM component here? Is there a GM component from V in to V out?
Because that is a very high impedance node.
So what will be the current path? V in to V out. That
RDS
means
of
your
the
yeah. So you have to assume here finite RDS. Otherwise, your PSRR will be infinite here. Huh? You will get an infinite rejection, which means whatever you signal, AC signal you have V in, nothing will appear at V out, which is not true, obviously, because that is the ideal case. And the reason we didn't consider the current, if you remember in the PMOS, we took only GM component. We didn't take R out component there because R out component would be much smaller compared to GM. So we completely ignored that. But here there is no GM component, so the only component is R out component here. So we have to consider that. So we'll see the effect here. So since you don't have a GM component, so intuitively you can tell the PSRR would be much better. But we need to see what exactly it is. So if I call it RON, so intuitively, if you want to look at it, so how much portion of Vin will appear at the V out? Let's say you don't have any suppression from the feedback. Just think about an open loop.
Sir, R load by R on plus R load.
Yeah, if you no R load, obviously you R load in parallel with R1 plus R2, correct?
Yes.
So this is a resistor divider actually. So in open loop, V out equal to let me call it. So I'm just redefining the R here as a parallel combination of R load and R1 plus R2. Where R out is R load parallel R1 plus R2. Okay, and what will be this? It will be less than 1 or more than 1 V out by V in here, or the ratio of these resistor divider.
Less than 1.
Because
Less
R1
than
is
1.
large.
Yeah. And what was in the open loop? What was the output term, if you remember, with respect to V in PMOS? Anybody remembers? Think about, you have a PMOS, gate is shorted, and from V in to V out, you have a common gate amplifier. What's that?
GMR out, right?
Yeah, GMR out, correct. So GM2 are out. So which is obviously a gain factor greater than 1. So in the PMOS, your getting output was getting amplified, while in the NMOS, your output is getting suppressed. Correct. So this component is already less than 1. So even in the open loop, you're not amplifying your output. The whatever the component of your AC input you are getting in the output is always basically less than what you have input. So that means you will always get some attenuation here, even in the open loop. And when you have a closed loop, obviously it will make it even better. So V out by V in open loop equal to open loop this implies PSRR of NMOS is better than PMOS, and this was mainly because of GM component. Here you have no G. Okay, so now we'll derive this and see what happens. So which means when you go towards so when this appear in the open loop, uh, so this, is there any other component here, or are we missing something here? Can anybody tell?
So C out.
No. Forget about C out. We are now talking only about the DC, which will be the peak basically. The around UGB, when you will peak, your loop will be mostly broken. Huh? So you can assume that your gate is shorted to ground, and so let's do here. V in. So I'm just calling it R out. RON. And if this is grounded, let's do a small signal. So how many currents you have? How many currents we have? Can we tell? 1, 2, 3.
3.
3 currents too.
So first current is out over R out plus V out minus V in over RON. Which is the third current? Can anybody tell?
The NMOS current.
No, RON is also NMOS current. Huh? RON is part of NMOS. I'm just showing a that is the intrinsic. Yeah, GM. Okay.
G. So
V
minus
out GM2. Correct. Okay. So I've changed the direction of the current. That's why it's plus. So don't get confused with that.
yeah. That's what I'm thinking.
Yeah. So so now let's see what you get. V out 1 over R out plus so we'll just simplify this, and what you get is okay. So let's write it. R out over R out plus R on. So this becomes 1 over 1 plus GM2 R out RON plus R out plus RO. Okay, so which means what does it mean? And if you consider this term, I mean, this term is much larger than 1, and obviously it would be because you are getting R out into R on in multiplication. So what you get here actually, this will cancel out. So approximately you can say R out divided by GM2 R out R, and this cancels out, and what you get is 1 over GM2 R1. So this is just approximation. Okay. So which means when we took this voltage divider, this guy, this one, So we are not considering the GM component. And what the GM component will do? What would happen? So let's say something appears in the output through this R on, and that will get divided by the divide ratio. Some voltage will appear here at this node. What will it do basically? Can anybody tell what will happen to that?
The change will get multiplied by the GM2 and will appear at the output again. Means,
So what will be that? It will be higher, lower?
it will be probably equal to 1.
No, why 1? So if you give any change at the source of this, what will it try to do? What, I mean, is there any feedback, local feedback here? When you are talking about the source follower, you are applying the input at the gate and then you are looking at the output, okay? But in this case, your input, output both are at the same node, V out. So what would happen if you make any change in the V out? What will happen? What will this NMOS try to do?
It back to the same node, so kind of.
Yeah, so it will oppose that, correct?
Yeah.
So any change when it is opposed, what do we call that? What effect is that actually?
Feedback.
Negative feedback, correct? So the source follower, that's the advantage of the source follower, that inherently you have a negative feedback from source follower. That means any change in the output will be suppressed by the gain of your source follower, and the gain is nothing but GMR out. Okay, so you get a two suppression here. One, obviously, whatever Vin is appearing, the only portion that can appear at the output is through this resistor divider, and then that will further get suppressed by your NMOS gain, inherent gain, which is GMR out. So, and that's why in the worst case, when you are assuming this, basically, if let's say all the signal is appearing, when I say all the signal is appearing, you assume that your I mean, in what case all the signal will appear at the output? When your output impedance R out is much larger than RON, then in the worst case, what will happen? It will be at least suppressed by 1 over GM2 R on in that case, or I would say R out actually, not R on. I think the approximation may not be very accurate, but let me just write it. So any change in V out due to V in is suppressed by inherent gain of NMOS. Okay. So, or you can say local feedback. And that's why you say when your source follower looks like a buffer, unity gain buffer, and if you take an op amp and connect it in the unity feedback, negative feedback with the unity gain, basically beta equal to 1, then the response will be similar to your source follower. Only thing, your DC voltage will be shifted, obviously, because of VGS drop. And which means your this source follower has an inherent negative feedback. And if your gain is very high, which means if GMR out is very high of this transistor, then it will behave like a unity gain buffer. Okay, so which means any change you make at the output will get suppressed by your loop gain, and the loop gain is nothing now here in this case will be GM R out of this output stage. Okay, so now if I want to,
Sir, I have a
want to,
question.
yeah, if
So can we intuitively also say that NMOS has a better load transient because there is inherent feedback because source itself is at the output node, right?
so your low transient will always be better because your output impedance is low, and this low output impedance effect is only coming from that your inherent feedback actually. So, but intuitively, when we say, okay, looking at the source is 1 over GM, that is only because when you do small signal, you will see this local feedback will make it 1 over GM. So now your PSRR is better, obviously, and which means when in the open loop your PSRR is better. So if you remember in the other case, your PSRR was 1 over GM of GM into R out of your first stage. Basically the gain beta 1 over beta GM1 R gate, or I would say 1 over beta AO1. And we were saying that your second stage will have no impact on your PSRR. That was mainly because of your GM component. So in the DC here, so if you say that it is suppressed by 1 over GMR out, and but this component is already less than 1, so you can say that, okay, even at DC you are starting with a better PSRR. And what will be the max when you hit around UGB? So what will happen? Can anybody tell?
By GM2, right?
No. What will be the DC PSRR here in this case? So in the open loop, you already calculated how much suppression you are getting. And when you close the loop, what will be the PSRR? Hmm.
There will be this additional beta AO1 R gate component at the gate of the NMOS, which we have to take in the equation.
Okay, so beta I naught, which means the gain of the first stage, correct? When you say additional component is what? So in closed loop,
I mean that GM2 VGS of the NMOS, that VGS initially the gate was at 0 and the drain was at, I mean source was at V out. So now the gate potential will change to feedback into that voltage.
by the gain of error amplifier. Okay. So you guys can do this. Verify this. I'm just directly writing this RON multiplied by 1 over beta I naught. This is your PSRR DC. A naught is your GM1, R gate, and GM2 R out. So this is the additional factor you are getting here. If you remember in the PMOS, only GM1 R gate was appearing in the gain, and you had a beta factor is common to both. But in this case, just GM2 R out is because of your source follower. So your PSRR, even the starting point, that DC will be much better. Whatever the intrinsic gain of your NMOS, that will also appear. Not the intrinsic gain, but the intrinsic GM multiplied by your R out, whatever the output impedance you have. Okay, so now let's do this plot. So PSRR magnitude. So what is the starting point? Can anybody tell? That was R out over multiplied by 1 over beta GM1 GM2 and this beta I naught, don't get confused with the loop gain here, because loop gain here is only the gain of your error amplifier. So A01 beta A1 will be your loop gain, but in this you are getting an additional factor of GMR out. That's why I have written again A naught here, which was the loop gain of your PMOS case. GM1 GM2 R gate. So we need more space. So let's say this is my dominant pole, which is your what will happen after here? Will it start or increase or decrease? Which direction it will go?
Become GM2 R on. I mean 1 by GM2 R on. And it will increase.
Yeah. So if this is your UGB, so your beta GM1 R gate is your loop gain. So leftover component will be 1 over GM2 R out multiplied by R out over R out plus R on, obviously. So this R out is basically when I'm writing R out, this is based on the assumption that your RON is much larger than R out. So when you have in the gain, you have a parallel combination of the two. So R on can be neglected. So, but if your R out is much larger than RON, then this R out will be replaced with RON. But and if you want to look at the total effect, then it will be parallel combination of R out and Rn. And then you have a second pole, which is your omega P out. And then you get your. So obviously, if you look at this term, where were we going in the PMOS? Anybody remembers what was? PSRR?
It was GM2 into R out.
Correct. So even if you ignore this this term, I mean, if you ignore this term, then it's 1 over GM2 R out. In other case, you are getting GM2 R out. So that's the difference, is exactly inverted. So instead of a gain, you are getting a suppression here. So that's why your PSRR inherently, even at around UGB, will be always better, or the suppression you will get always more than 1 here. In the other case, your suppression was, instead of suppression, you are getting a basically amplification. So now if let's say GM2 R out is roughly 10, though obviously you can say, okay, and whatever factor you get from this resistor divider, you can say even around UGB, my PSRR will be minus 20 dB or higher. And if you talk about the DC PSRR, is obviously much higher. If you are getting a, let's say, minus 60 dB in PMOS, then you would get roughly minus 80 dB here in NMOS. So both DC and high frequency PSRR looks better in this case. Any other benefit do you guys see? Can anybody tell, is there any impact on UGB in the NMOS compared to PMOS?
It's large, right? Because R out, I mean, is lesser. I mean, 1 by GM.
Yeah.
So inherently, it will be larger.
Yeah, so your non-dominant pole, which was at 1 over R out C out, now it is pushed to GM2 over C out. So that will obviously be at much higher frequency. So now you have a room to increase your omega UGB, which means you will require lesser cap at the gate, compensation cap, and you can get extended bandwidth here because your omega P out is pushed at higher frequency. So in terms of bandwidth also, you get advantage here. Your PSRR is better, and when PSRR curve is better, obviously you can say line transient will also look better because you don't have any GM component. So any fast change in the in your VDD will be completely suppressed here. While in the other case, any fast change in the VDD will appear at the output because your loop may not be able to respond that quickly. So if you give any step at the input, the large component will appear at the output in PMOS compared to NMOS, because NMOS, we know that there is no GM component, and this R out, basically the R out component will have some suppression. And then on top of that, you have a inherent negative feedback from NMOS that will further suppress it. So your line transient is better, load transient is better, your both line and load regulations are better, your bandwidth is higher. So all benefit you get from NMOS regulator. So if I want to summarize here, so NMOS LTO. Better load and transient response. Better load. So the only drawback is
High dropout voltage.
high dropout voltage, or error amplifier would require a separate VDD. Higher VDD for low dropout. Okay, but in most of the cases when you are designing, let's say for the load 10 milliamp or so, the benefit you get in terms of area. Let me, I forgot to mention one more point. Smaller size of pass element. Okay. So let's say, I mean, majority of the, if you say the total area will be, I mean, 50 to 60% area of the total LDO will be taken by your pass transistor. And then second major component will be your compensation capacitor, basically. So compensation capacitor, basically you'll have in both the cases, PMOS and NMOS. But whatever area saving you get, now let's say even if you have to use a on-chip charge pump to boost your supply, the total area may remain same. I mean, when you compare the PMOS versus NMOS, if you don't use charge pump, obviously it will look smaller. But once you use the charge pump, that is the additional component you require for NMOS LDO. And then that will have some additional capacitor and switches. So it will make your size of LDO bigger. But when you compare with the PMOS, because your PFET size was 4 to 5 times higher there, so the area may be comparable. So with a comparable area, you are getting all these benefits. So in that case, uh, basically you can say that NMOS LDO performs better in terms of your different basically performance metrics, whether you what you call load and line transient, your regulation, your in terms of bandwidth, and even if you have to use a on-chip charge pump, your area may be comparable to PMOS. So that's why NMOS LDO is most popular, especially in all low noise applications and all those where you require very high PSRR, where your supply is little bit noisy. And we know that when your LDOs are hooked up at the output of your switching regulators, it will always have a ripple in the input or VDD, and you need to suppress that. So for noise sensitive application, let's say RF or your biomedical applications, where even a 1 or 2 millivolt ripple in the output may not be acceptable, then NMOS is a better choice over PMOS.